So in the last class, we had derived the creeping flow equation. So the creeping flow equations are minus gradient of P plus mu times the viscous term equals 0. So in case we look at a dimensionless form of this, we had this. And in this particular case, the viscosity simply vanishes and I have not put the over bars on the variable. So this is the dimensionless form. So let us look at certain characteristics of such equation. So first of all, this equation is linear in pressure and velocity. There is no nonlinearity. The nonlinearity in the Navier-Stokes equation comes from the advection term. And this advection term being 0 in creeping flow renders the equation linear. So let us consider a very simple case, that is the flow past a body and its mirror image. Let us first have a look at what your preconceived notion may suggest. Let us consider a body which looks like this triangle and assume that the flow is from this direction. Say that the flow magnitude is u. Okay, so for this particular body, there will be some drag acting on the body. So let me call that as Fd. But what happens if I now reverse the orientation of the body? I make something like this, and I have the same incoming velocity to this body as well. What is the drag acting on the body in this particular case? So if I call this A and if I call this as B, the question is the drag on object A larger than, equal to, or smaller than the drag acting on the object B? So general notion from high Reynolds number fluid mechanics, such as streamlined cars and all those, it suggests that object A should have a lower drag as compared to object B. Object B is more like a bluff body, whereas object A is more of a streamlined body, right? So the streamline will go like this and try to recover like this, okay? And if the velocity is too large, there will be some separation eddies over here. Whereas in this case, if the flow will directly become turbulent like this, there will be large separation eddies over here. So this is what you know from high Reynolds number fluid mechanics. However, in the case of low Reynolds number fluid mechanics, this is not necessarily the case. Let us see what happens. So let me just copy this image. Now let me draw it again. Let us say we have a coordinate system like this, x and y, and let's say the body is like this, and the velocity is uniform incoming into the object. So the governing equation for this is this is the governing equation for the flow along with the continuity equation. So equations 1 and 2 are subjected to u equals 0 on the surface of the body. So essentially u equal to 0 means no penetration and no slip on the surface. So S represents the surface. Okay. and the other condition is u equal to capital U times Ex as mod x tends to infinity. So mod x means the distance from the origin. So this is the origin. So mod x represents the distance from the origin. So for large distances, we should have a uniform flow which is in the x direction. So this particular set of equations, if we are able to solve, we will obtain the drag acting on this object. If we look at equation 1 carefully, we see that if we substitute u by minus u and if we substitute p by minus p, we recover the same governing equation. The governing equation is still, so let's say I replace u by u tilde or u hat or rather u tilde and p by minus p tilde. So the minus signs are cancelling out because of the linearity and we still obtain the same equation, meaning the transformation of u to minus u and p to minus p recovers the same equation. Similarly, this is also 0. Okay. So let us try to draw what this actually represents. So let us write down the boundary conditions also. U tilde is 0 on surface, while u tilde will become minus u Ex. Right. So these are the governing equations and these are the two boundary conditions. So what physical situation do the equations that we have obtained by making a transformation u as minus u and p as minus p represent? So given the fixed coordinate system, we have reversed the velocity. So the coordinate system and the object remain the same, but instead of having a velocity in the plus x direction, we now have a uniform velocity in the minus x direction. The solution for this particular problem is simply the solution of this, but the sign of velocity reversed and the sign of pressure reversed. So with this information, let us see whether we can estimate what is the drag. So first of all, how do we find drag? So the force vector, as we know from very elementary classes, is the integral over the entire surface of the stress tensor dot n dA over the entire surface, where in general the stress tensor is minus p times the identity matrix plus mu grad u plus grad u transpose, right? In a dimensionless form, this is also minus p times the identity matrix plus grad u transpose. So the reversal of sign of p and u causes a direct reversal of sign for these terms, and so the reversal of sign leads to a reversal of tau. So if the reversal of u and p leads to a reversal of sign of tau, while the n and the dA are still the same, it means directly that the f will have the same magnitude, but the direction will change. So this is contrary to our understanding of higher Reynolds number fluid mechanics. So the drag acting on this body and this body is identical. In a given flow, the drag acting on these two objects in this uniform flow are identical. And let us see what the genesis of these drags being equal is. Rather, let us see why the drag is not equal in the case of higher Reynolds number fluid mechanics. So in higher Reynolds number flow, you have the term rho u dot nabla u. So this particular term is not going to change if you replace u by minus u. So the effect of this particular term is to sort of always have a net dissipative effect on the nature of flow. So in case of low Reynolds number flow, the particle moving along a streamline like this has no trouble in going back to this position. Whereas in the case of high Reynolds number flows, a particle, if it goes like this, inertia will try to keep taking it along this trajectory, okay, while it will not be able to recover to this position. The lack of recovery in this position will cause a circulation around here, and thus it will lead to an eddy formation. Even in this case, so this particular streamline in this kind of flow and the reverse streamline like this, they have the same energy penalty and they are not different in case of Re equal to 0. The fact that the nonlinearity is causing the lack of recovery of a streamline is what is absent in Re equal to 0 flows, and thus the drag acting on an object which may have a seemingly bluff body or a streamlined body is identical in the case of sweeping flows. So this is a very important conclusion because it goes against our preconceived notion. Now let us move on to the second case, that of the drag or the lift acting on a sphere in general linear flow, and the sphere is also rotating. So sphere, the rotating sphere in a linear flow. So what is a linear flow? So a linear flow is something which depends linearly on a coordinate. So let us see. So first of all, we have seen earlier that this is a uniform flow. This is a uniform. So a linear flow is something which depends on the local coordinate. So it can be something like this. So if this is the x coordinate and this is the y coordinate, such a kind of flow is given as u comma v is equal to some gamma y comma 0. So as y increases, the u velocity increases. So this is what we have shown in this schematic. And as y becomes negative, the u velocity becomes negative. So this is a kind of a shear flow. There are various kinds of linear flows and we will not discuss them over here. There is a entire discussion on this for understanding chaotic flows and all. So let us consider what happens when we add this kind of flow and this kind of flow. So obviously this point of 0 velocity will shift lower because you're sort of adding this positive velocity to this negative velocity. So the location where the 0 velocity will occur will shift downward. So if this is the particle at the origin, so we call this as x and we call this as y. So then this particle is sort of immersed in such a kind of flow. Okay. And this particle is also rotating. So let's say the rotation vector is this. So it's obviously rotating along this axis. So the question is, in such a kind of linear flow, if we have a rotating particle, what is the lift? So the lift acting on this object. So the lift in the y direction. So what is the lift? Let us consider the following. The equations once again are linear. So the equations are minus grad phi plus nabla square u equal to 0. So I have written on the dimensionless form. So what will be the boundary condition? So let us write down the continuity equation. So these two are the governing equations. So the boundary condition will be u equal to omega cross r on the surface. So this is the local velocity on the surface, right? Relative to this coordinate system attached to the center of the particle, this will be the velocity of the particle. What will be the other boundary condition? That u will be equal to the uniform velocity plus, so uniform velocity in the x direction plus a linear shear. So say the coefficient is gamma times y in the x direction. And in general, we can sort of write a dimensionless form in the following manner. So it can be 1 plus gamma tilde times y in the ex direction, where gamma tilde will be equal to gamma divided by u. And the dimensionless velocity will be u vector divided by capital U. So this is sort of the dimensionless way of writing the condition at the far field. So this will be the condition as mod x tends to infinity. Far from the particle, this is the imposed velocity, this particular velocity. Now, because the equation is linear, we can perform a superposition of the three fields. So the superposition is comprised of three different things. So the first thing is a uniform flow. The second thing is a linear flow. And the third thing is a particle rotation. So for all these three superpositions, the Gurney equations are still the same. But in this case, let this be u1, let this be u2, let the velocity be u1, u2 and u3. The total velocity u will be u1 plus u2 plus u3. So the Gurney equation for this will be minus grad p1 plus nabla square u1 equal to 0, nabla dot u1 equal to 0. Similarly, for the linear flow, the Gurney equation will be the same, except for the subscript 1, there will be a subscript 2. Similarly, for this, the equation will be the same, except that instead of subscript 1, there will be subscript 3. So let us see whether we can, from symmetry, understand whether there will be a lift acting on the body. So the first superposition, that is the uniform flow. Because the particle is symmetric about the x-axis, we expect that the streamline be like this, and there will be no lift acting on the object. There will be no lift acting on the object by symmetry. What about the linear shear? Now, because we have decomposed, because we have decomposed the uniform velocity from the linear shear, it's as if this particular point is at the object center. So, can there be a lift in the case of a linear flow? Suppose that there is a net lift in a shear. Suppose that we say that in this top half there is a net lift in this direction. But this bottom half is literally the minus version of this. And like we have seen in the first example, if the velocity is minus of this, then the lift will also be minus of this. So if there is a lift in this direction in this top surface, there must be a lift on the bottom surface in this direction. And they must be identical, otherwise we will violate symmetry. So there will be no lift because of this symmetric condition where u substituted by minus u on the bottom half nullifies whatever lift there could be from the top half. Hence, linear shear also causes no lift. What about the rotation? What about rotation? This is the rotation axis. So obviously rotation about this axis will cause the shear stress to be equal and opposite from the two hemispheres, because it's a pseudo vector, that is rotation from this when seen from this side and from seen from this side are opposite. Whatever sort of lift this surface will try to create in this direction will be the same that it will try to create in this direction, and there is no sort of tendency for the object to move in a plane which is orthogonal to the vector of omega. So this particular plane is sort of the plane which is orthogonal to the vector of omega. So we want to understand whether there is any movement because of the vector omega in the plane orthogonal to omega. We know that there is no movement of the object along the direction of omega because the top rotation and bottom rotation will cancel. But whether or not there will be motion in the plane orthogonal to omega is not known. But because each direction of the orthogonal plane is sort of identical, there cannot be any bias which the particle can have in its movement orthogonal to omega. Hence, no movement along omega and no movement orthogonal to omega. And hence, there is no drag or lift because of rotation. So, we have seen two very fundamental arguments which essentially stem from the linearity of the problem, that given a particle which is rotating in a linear flow, in a general linear flow, there will be no lift. This also goes against our common understanding of high Reynolds number fluid mechanics. The understanding is, if we have an object which rotates, and everyone might recognize this as the Magnus effect. If there is a net rotation, there is a net lift. Okay, and this net lift is also a consequence of the presence of the inertia term. The lack of this non-linearity does not allow for the problem to have a departure from symmetry, and thus there is no lift. So, high Reynolds number fluid mechanics, if you impart spin to the object, there will be movement, and this is, everyone knows this from cricket. So, spinners will have a sudden dip in the ball. That is the reason why they flight the ball. So, they can deceive the batsman in flight. So, if you spin the ball, there will be a very drastic dip in the ball, and this is what many good spinners are able to exploit. But if you were to play cricket in a pool full of honey, you probably wouldn't be able to exploit that same phenomenon, because you will achieve nothing. Okay. So this was the second phenomenon. So let us proceed to one of the last, rather impactful phenomenon, that of a lift in a Poisel flow. Let us consider a Poisel flow. This is a Poisel flow. And if we have an object in a Poisel flow, the question is, if the flow is a creeping flow, is there a net lift on the object? So let us take a small digression to the very famous article by Segre and Silverberg. In the article of Segre and Silverberg, they observed that if you put particles in a Poisel flow, the particles all tend to agglomerate at a distance approximately 60% from the radius, from away from the center line. So if the particle is over here, it will try to migrate over here. If the particle is here, it will try to migrate over here. So they saw this phenomenon. So observation was obviously that yes, there is a lift, but whether or not creeping flow is the reason for that lift was debated. Many people did try to explain this particular observation from creeping flow, and they were not successful. They were able to show that in creeping flow there is no lift acting on an object even if it is in a Poisel flow. Let us see whether we can arrive at the same conclusion without actually solving anything. That is where the fun lies. So let us draw again. So suppose that there is a net lift like this. In this kind of Poisel flow, we assume that there is a net lift like this. We attach a coordinate system on the object. So this is xy, and we assume that there is a lift in this particular direction. Now, if I reverse the flow, so I represent u by minus u. Essentially, I am solving a problem like this, where the coordinate system is still fixed, but the incoming flow is this instead of this. So this is the minus u incoming velocity. And if I do this, we recollect that if the governing equation is the same, then P must be also minus P, and the drag and the lift will also change sign. So this particular introduction of a negative velocity would allow me to have a lift in this direction. But see, the mathematics tells me the lift is in this direction, but the physical situation remains the same. The physics of the problem should not be dependent on my choice of coordinate system. So a flow coming from here is also equivalent to a flow coming from here. There is fundamentally no difference. So thus, because we have a paradox that a flow from this direction causes a lift in this direction, but the flow from this direction causes a lift in this direction, these two things cannot be simultaneously valid, and hence there must be no lift on an object in a Poisel flow. And this is actually true if you consider the case where inertia is identically equal to 0. But what about the observation of Segre and Silverberg? So many years later, Ho and Neal, they were able to show that whatever migration of the particles that Segre and Silverberg saw in their experiment was due to weak inertial effect and possibly the effect of the bounding wall. Because as the particle goes more and more towards the wall, it will sort of not be an unbounded particle and it will start seeing effects of the wall. So the weak inertial effect is what causes migration of the particle. But what is actually the weak inertial effect? We recall that creeping flow is when Re is identically set to 0. But when Re is much smaller than 1, then Re acts as a perturbation parameter. And setting Re equal to 0 is sort of the base behavior of the equation for low Reynolds number. Let us see whether we can quickly see what will happen if we take low Reynolds number. So we have Reynolds number times, so let's say the flow is steady. Let us assume that the flow is steady. U dot nabla U is equal to minus grad P plus nabla square U. We can assume that U is U0 plus Re U1 plus Re square U2 and so on. So this is a very naive algebraic perturbation, but they may not be necessarily in this particular form. But anyway, for this particular argument, it holds. If we substitute this particular form of velocity in this equation, right, and we expand all the various terms, so this nonlinear term will give us cross couplings of u0 and u1. u1 and u2, u0 and u2 and so on. Well, these terms will have no such cross coupling. So if we collect order 1 terms, we will have minus grad p0 plus nabla square u0 equal to 0. If we take order re terms, then we will have the contribution from this term and this. So this will be minus grad p1 plus nabla square u1 is equal to u0 dot nabla u0. If we take order re square terms, the left hand side will be minus grad p2 plus nabla square u2, while the right hand side will be, so we have to construct re square from the right hand side, but there is an re already appearing over here. So we have to choose all the parameters which are re times something over here. So u multiplied by u, what will be re? So it will be u0 times u1. This particular term will be order re. Similarly, so that will be the only term. So we will have u0 dot nabla of u1. Okay, so this will be the first sort of influence of the cross coupling. So something like this happens, and at higher orders, the lift happens to be non-trivial, and that particular lift is what is able to explain the migration of particles as seen by the experiments of Seger and Silverman. But the important point is, we were able to conclude a very important solution, that a particle, if it is described by creeping flows, in the case of a Poisel flow in the background, that particle has no lift. It is higher order effects which actually cause the particle to have a net lift. In fact, if the fluid is non-Newtonian, then also the particle has a net lift. If the particle is non-spherical, then also the particle can have a net lift. But for a spherical particle in a Poisel flow, there is no lift, and this is a direct conclusion from the linearity of the problem. Okay. What happened? Yeah, I mean, you just have to expand this. All the re square terms will start appearing. Okay. So I just quickly written down the expansion, but I mean, you have to do it. Actually. So with this, I conclude this particular micro lecture, and we'll continue with the two-dimensional creeping flow solutions tomorrow. And these solutions are very important for us to learn because they are flows in slots, and what Moffat had theoretically predicted about his vortices in slots was actually later verified in the case of creeping flows, and that signaled a very big victory for creeping flows and how they can be applied to actual processes. Okay, so I'll see you tomorrow.